Hello, welcome back to CS128 Honors, and today we'll be covering an introduction to threads. So, we'll cover some OS concepts like processes and threads. Then in Rust, we'll cover how to use threads and how to manage data movement between them. And to read more, you can read chapter 16.1 of the Rust book. So, operating systems. You probably know the main three, which is Windows, Mac OS, and Linux. Their role is to manage the CPU, the main memory, disks, and other resources, and to abstract out system functions to different hardwares so that programs don't need to know exactly how to interact with each specific disk, for example. So, what is a process? A process is an abstraction of a single program, and you can have multiple threads and processes in the same program. Like for example, Firefox is a single process, Discord is a single process. And what is a thread? A thread is a single line of execution, and you can have many of them in one process. These threads share the same memory space, so they have the same access to memory throughout the system. But this is often unsafe, so Rust doesn't let you do it exactly like that. And in Discord, an example is that you have a thread for listening to messages, so pinging which ones are coming in. You have a thread for listening to the keyboard presses. Like for example, you have one reading your chat messages, another pulling notifications from the web, another drawing out the UI. Yeah. The operating system is responsible for scheduling each of these. And if we don't manually tell the OS what to do, like when to schedule a thread, when to stop a thread, when to wait for a thread, the OS will do it in whatever fashion it desires, which may not work with what we're trying to program. Threading, especially memory safe threading, is really difficult. Rust has a way to help this, but there's still problems you can have, even in Rust. Like for example, deadlock, where thread A waits for thread B, while thread B waits for thread A. They're holding resources that each other need, but they won't free them until they get the other's resources. With threads, often you can get something called a race condition, where one resource is accessed by one thread or another, and they're competing to use the resource. But it's non-deterministic, so it might happen, it might not happen. So these are hard to reproduce. So let's cover race conditions, right? Say you have a bank account with 100. Two people decide to deposit 80 at the exact same time. And you'd think if two people are depositing 80, you'd have 260 when you're done. So they go at the same time, they check how much it has. So they both check and it says 100. So the bank tells them 100. Then friend A's ATM adds 80 and gives it back to the bank. But thread B's ATM also reads that it's 180 and returns that to the bank. So you gave 80 twice, but your bank number only went up by 80 bucks. Since the second ATM here doesn't know the first one updated it, so it returns its updated value and overwrites this, essentially not changing anything. So these race conditions are very common when you are working with threads, and Rust uses ownership and types to help prevent these problems. This is called fearless concurrency. So today we're covering how to make new threads, and soon we'll talk about more advanced concepts. Okay, so here we'll cover spawning a thread. You can use the std thread library, standard library, and for this example we'll also be using time duration. So to spawn a new thread, use the spawn method of the thread class. Use this closure syntax to where it takes in 0 parameters and you plug it like this. You move 0 values into it. We'll talk about that shortly. But this body here is what the thread runs. And 10 times it'll sleep for 1 millisecond. Okay, so when you spawn a new thread, the main thread continues. So the main thread is the one that runs all these commands first, and then the new thread will run just this. So the spawn thread will branch off the original one, running essentially in parallel, or the illusion of concurrency. We can discuss that in a future lecture. But they run at the same time and don't know exactly what each other are doing. So this comes to the problem which I'll demonstrate right now. I have an example code here from the previous one where I have a handle here, a thread spawned like this. Then I run it for 10 iterations. I sleep for a millisecond, and then this thread would close. But in the same time, I'm printing to the main thread here. So let's see what happens when I run cargo run. You'd expect that it does this, and it also prints this 10 times, right? That would make sense. So I run it. Only it happened one time. That's weird. Why didn't it all happen? Let's try it again. This time it didn't even finish. This time it was only hello from main thread. What's the problem here? Problem here is that the program ends when the main thread finishes. So anything that isn't finished by handle A by the time this function ends will be killed, so it won't happen. Like here, it got killed mid-print. By the time it got to here, it was gone. So, what's this problem? We noticed that it never got to finish. This is because the main thread finished before the child thread. How can we solve this? We can do something called joining the thread. So we're waiting for it to finish. Like this. You can join it, and then we can unwrap later, but I don't need it for now. So, yeah, whatever. Join returns, why is it erroring out? Yeah, join returns a result of type whatever the thread should return, which this join handle is a unit type, so it doesn't return anything really. So we can just unwrap it anyway. So, after it prints hello from main thread, it'll wait for handle A to finish, like this. Let's run it again. And look, it prints 1 through 9, which is what we did here. Let's just make it 1 through 10 just in case. And yeah, see, it prints 1 through 10. Without this handle, join, it won't wait for the executing thread to finish before it kills it. Just like this, the parent will wait until the child thread will finish, and then it'll continue any execution under this. Like for example, if I were to write like this, then once I run it, after number 10 is printed, then main thread will print finished. So yeah, that was the demo. Then how can we use data from the main thread in the spawn thread? So you have this handle here, and you want to give it something to run with, but from our current thread. You want to give it this vector. By default, if you just have it like this, Rust will try borrowing the vector. However, this thread may outlive the current scope of the function, which will make it so that Rust drops the vector, but this already has it, so it's illegal and unpredictable behavior. So, like for example here, as I mentioned earlier, when it drops it like this, what if this drop runs before the println statement? So that would mean that this vector is no longer valid memory like this, and it'd be undefined behavior. So like this, Rust lets you move it into thread into the new thread instead of borrowing it. This makes it so that you can't use it even after this handle. This ensures that there's no invalid memory, or invalid memory reads or writes after. So, in summary, processes and threads. Processes are like applications running on your computer. Threads are a single line of execution, and a process can have multiple of them. You can spawn a thread using thread spawn. You must wait for a thread to finish before killing your program, or if you need to, by using handle.join for any handle. Then, to move any data into the new thread, you can use the move keyword when passing it to the closure. And some announcements. Homework 10 will be released today on PrairieLearn. It will be due next Friday, and we will be releasing the final project specifications, so start thinking about groups and project ideas. And the drop deadline for the course is tomorrow, as for all courses. All right, thank you for watching.